The theory of quantum physics states that particles can be in different states at the same time and communicate over exponentially large distances. In the 1930s, Albert Einstein said that this was spooky action at a distance. In order to understand why, let's take a look at some of the ideas presented by this theory.
All fundamental particles have a property called spin. They're not actually spinning, but it's a good way of thinking about it. Instead, it's a combination of angular momentum and orientation in space. A particle can either be spin up or spin down. For our purposes, spin up will be red and spin down will be blue. Particles can also be entangled, which means that when one particle is red or spin up, the other has to be blue or spin down, and vice versa. Quantum physics says that both particles exist in both states at the same time and have a 50% chance of being red or blue at any given time. That is, until you measure them. Two quantum particles can become entangled if they originated from the same particle or source, or if they interact with each other. If two particles are entangled, when you measure one of them, the other one will instantly settle into the opposite state, no matter how far apart the particles are. So when one particle is measured, and its spin determined, you immediately know what the spin of the other particle will be. Einstein was not a big fan of this idea, as it implies that these particles are communicating faster than the speed of light, which went against his theory of relativity. Instead, he believed that there were some hidden variables within the particles that allowed them to communicate. However, in the 1960s, John Bell proposed a testable construct to resolve the argument between Einstein's classical approach to the idea of locality and hidden variables and a quantum explanation for entanglement. He called this the Bell test. There are two loopholes with the original Bell test. First, the detection or unfair sampling loophole, which says that it is hard to detect all of the photons that we want. Second, the locality or communication loophole, which says that it is difficult to get two entangled electrons far enough apart to prove that they aren't communicating by means other than quantum entanglement. In 2015, scientists came up with a loophole-free Bell test, using both photons and electrons. They began with two unentangled electrons that were 1.3 kilometers apart that existed in both states at once. The scientists entangled each of these electrons with photons, and then subsequently entangled the two photons. So now we have an electron that is entangled with a photon, that is entangled with a different photon, that is entangled with a different electron. Now the two electrons are both entangled and far enough apart to avoid the second loophole. The scientists measured the state of one electron and observed that it did in fact instantaneously determine the state of the other. So Einstein was actually wrong. Does this mean that we can send messages instantly across the universe? In short, the answer is unfortunately no.
If not anything else, this would make Albert Einstein happy.